In this video, we're going to show that homeomorphism preserves the Hausdorff property. So we're going to start off with some definitions here to get up to speed with what Hausdorff meant again and what homeomorphism means again. So if you've got a topological space xt, we're going to say xt is Hausdorff if for any distinct points x and y in your set x, there exist two sets in the topology, so two open sets u1 and u2, such that the following happens. Such that the intersection of u1 and u2 is the empty set. In other words, u1 and u2 are disjoint. And then x is in u1 and y is in u2. So in my picture, you can kind of think as Hausdorff is saying that we should be able to separate any two distinct points with open sets. Now be careful. Some might shorthand this and say that x is Hausdorff. When people say this, it's understood that this means that the topological space xt is Hausdorff. In other words, I'm trying to say that topology is important. It doesn't make sense to just say a set is Hausdorff. And so the topology T is crucial. And to try to demonstrate this for you, I've got two examples we're going to look at. Let's say I take the same set, which is the real line in both examples, but let's change the topology between the two examples. In the first example, I'm going to take T to be the usual topology, which means that open sets are arbitrary unions or intersections of finitely many sets of the form A comma B, with parentheses on the left and the right. And that indicates in college algebra, say that you don't get the endpoints. In the example to the right, we're going to take the trivial topology on the real line, which says that we're only going to have two open sets, the empty set and the whole set X itself. Now let's go back to the left. The real line with the usual topology that we're used to from algebra and calculus is a Hausdorff space. And to see this, let x and y be two real numbers that are distinct. And let's just measure the distance between x and y and cut it in half. And what I'm going to do is I'm going to make a set centered at x of that radius, go that many units to the left and that many units to the right. And similarly, go that many units epsilon to the left of y and that many units to the right of y. And I've just got a picture there of what these two intervals would look like. And the point is that they don't overlap anywhere. So these two intervals here separate x and y. So since x and y were arbitrary, we could do that for any two real numbers on the real line. Therefore, xt is Hausdorff in that situation. But if we go back over to the example on the right, that copy of the real line with the trivial topology is not a Hausdorff space. And the problem there is that if you give me two distinct points x and y, there's not enough open sets to separate x and y. The only open set that contains x is the whole set x, but that set also contains y, so it's impossible to find a set in T that separate x and y. So again, just demonstrating that if you change the topology, then all of a sudden, this topological space might not be Hausdorff, even if it's the same underlying set. Now let's get to our next definition from one of the buzzwords in this video. Let's say you have a function between two topological spaces, x with topology T and y with topology T prime, or maybe you call it a map instead of a function. Who cares? We're going to say f is a homeomorphism if three things happen. The first thing is that f is bijective. Remember, that means one-to-one and onto. And then number two, that f is continuous. And remember, that means that for each set u prime and t prime, in other words, for each open set of y, the pre-image of u prime is open in x. In other words, f inverse of u prime is in t. And number three is just going the other way. The inverse of f is continuous. And what that means in symbols is for each open set of x, in other words, for each u and t, f of u, the image of u, is open in is open in y. So in other words, f of u is in t prime. And finally, we get to the theorem that we're going to look at that is, again, indicated in the title of this video. If you've got a function f between two topological spaces, that's a homeomorphism. And if you know that x with its topology is Hausdorff, then that guarantees that y with its topology is Hausdorff. So let's look at the proof of this. So what we're tasked with doing is to try to show that y with its topology is Hausdorff. So how you do this is you would let y1 and y2 be two distinct points in the set y. Now, since f is bijective, we know that there exist unique points x1 and x2 in the domain x, such that, the output of x1 is y1 and the output of x2 is y2. And I just got a picture for you over here, and we're going to add some stuff to this picture as we go. So remember, what we would like to do is to come up with two open sets over in Y that separate Y1 and Y2. So somehow we're going to use some information we know that's going on back in the domain X in order to come up with those open sets. And so here we go. The big thing that we know about X is that X with its topology is Hausdorff. So that guarantees us that there exists U1 and U2 that are in X's topology such that x1 is in U1, x2 is in U2, and U1 and U2 are disjoint. So here's my updated picture, and I'm just saying that I can find two open sets in X that separate x1 and x2. And so how do I get from the set X to the set Y? Well, I use this function f to do it. So naturally what you'd like to do is just apply f to everything. So we're going to apply f to those three statements from the Hausdorff criteria above. And we see, well, f of x1 is going to be an f of u1. In other words, y1 is an f of u1. And f of x2, of course, would be an f of u2. So that says y2 is an f of u2. And so what we're thinking is, one more thing before I get to what we're thinking. The empty set is the same thing as the image of the empty set, but I know that the empty set could be rewritten as u1 intersect u2. And I know that functions can split over intersections of sets. So that's the same thing as the intersection of f of u1 with f of u2. So if you put that big chain of equalities together, that says that f of u1 and f of u2 are disjoint sets, just like I've drawn in my picture. There's no overlap between the pink and the green. So the last thing that we need to do is, great, you found two sets that separate y1 and y2. How do you know they're open sets to do that? So remember, Hausdorff requires that these sets that separate these points be members of the topology. So how do I know f of u1 and f of u2 are indeed in T prime? But that's where, again, it comes down to f being a homeomorphism. And so how do I know f of u1 and f of u2 are in T prime? It's because I know f inverse is continuous. Remember, that's a consequence of f being a homeomorphism. And so that ensures that f of u1 and f of u2 are in T prime.